Okay, so we are going to put some calculations in math to what we know about light. And we're going to do this with two different relationships. Okay, there are going to be two simple algebraic equations with two different relationships. So the first one is wavelength and frequency. These notes are also linked in Classroom. If this is too small of a screen, you can also pull that up at the same time as you watch this video. Okay, so wavelength and frequency. We have a new constant here. Okay, so C, capital C, stands for the speed of light, and that is 3.0 times 10 to the 8th meters per second. Okay, it's a constant. It'll always be the same. That is always the speed of light, at least here on Earth. That is always the speed of light. Okay, so 3.0 times 10 to the 8th meters per second, always given to us, equals lambda, which we know stands for wavelength. Okay, so that Greek letter lambda is wavelength. The thing about wavelength in this equation is we always need it to be in meters. Okay, so if it is given to you in nanometers, which we know is another way that we can measure wavelengths, if it's given to you in nanometers, you need to convert that to meters. Okay, and we know that 1 nanometer equals 1 times 10 to the negative 9th meters. Okay, 1 nanometer equals 1 times 10 to the negative 9th meters. I don't care if you convert metric to metric and just move the decimal point, or if you would prefer to do dimensional analysis. Either way I'm fine with. To do dimensional analysis, you would be given the number of nanometers in the problem, and you would multiply by 1 times 10 to the 9th meters. That's how you would do the dimensional analysis for this. Okay, so that's wavelength. And then this fancy looking V is the Greek letter nu, N-U, nu. And that is our variable for frequency. And our unit for frequency, which we learned on, I think, Thursday, is hertz. Okay, so we have C equals lambda times nu. You'll always have C. You'll always have the speed of light. That's a constant. You'll be given either lambda or nu, or the wavelength or frequency. So then you're just going to solve for the missing variable. Okay, here's an example. Calculate the frequency of light with a wavelength of 575 nanometers. Okay, go ahead and pause this video and try to solve that. Okay, see if you can solve that. So, first thing you need to do. So the first thing you need to do is convert this nanometers to meters, because remember, we always need our wavelength to be in meters. Okay, so 575 nanometers, in order to convert to meters, okay, we have 1 times 10 to the negative 9th meters. You multiply the number of nanometers that you're given times 1 times 10 to the negative 9th meters, okay? And you should get 5.75 times 10 to the negative 7th meters, okay? That is our wavelength, okay? So we have wavelength. We have the speed of light. That's our constant, 3 times 10 to the 8th meters per second, and we're calculating the frequency. Okay, so it's just a simple algebraic problem. You have 3 times 10 to the 8th meters per second equals the wavelength that you just calculated in meters, and you're solving for V. Okay, speed of light, wavelength. The variable we're solving for, or sorry, not V, nu. The variable we're solving for is frequency. Okay, So you need to divide both sides by 5.75 times 10 to the negative 7th, okay, your wavelength. And you should get, your frequency should be 5.22 times 10 to the 14th hertz. Remember, hertz is the unit for frequency. Okay? All right, so that is wavelength and frequency. The second relationship I want to talk about is frequency and energy. Okay, so the new equation is E, so capital E equals lowercase h times nu. Okay? So E stands for energy of a photon. When I say energy, when we're talking about frequency and energy, I'm talking about the energy of a singular photon, one particle packet of light. Okay? And since that's energy, we know that the unit for energy is joules. So capital E, energy of a photon in joules, equals lowercase h. This is another new constant. So we learned the speed of light, that's capital C. Another constant that we're learning now is called Planck's constant, and that is 6.626 times 10 to the negative 34th joules times second. Okay, so we'll always have that constant. And then we have nu, or that fancy looking V, frequency in hertz. Okay, just like the previous equation that we just did with wavelength and frequency and speed of light, you have a constant here, so you always know one, you'll be given the other, and you're just going to solve for the missing variable. Okay, let's do a practice problem. Calculate the frequency of light with an energy of 3.6 times 10 to the negative 19th joules. Okay, we don't need to do any converting here. The only converting you need to do with these light calculations is between meters and nanometers with wavelength. Okay, and wavelength is not a part of this equation. Okay, so calculate the frequency of light, so we're solving for frequency, with an energy of 3.6 times 10 to the negative 19th joules. Okay, so plug in capital E, 3.6 times 10 to the negative 19th joules. Okay, equals Planck's constant. We know Planck's constant. It's given to us, 6.626 times 10 to the negative 34. Okay, and we're solving for frequency. Okay, so we have Planck's constant, we have our energy, and we're solving for V. And we do this by dividing by Planck's constant, just like you do in algebra class. Okay, and your frequency ends up being 5.43 times 10 to the 14th hertz. Remember, hertz is our unit for frequency. Okay, so our frequency ends up being 5.43 times 10 to the 14th hertz. Okay, so we have both of those equations. The only thing left to do is combine them. Okay, so here's an example. Here's both equations, okay? And the question is asking, what is the energy of a photon of light with a wavelength of 455 nanometers? So, we're asked for the energy, we're given the wavelength. Wavelength and energy are not in the same equation, okay? This is where we need to use both of them. What do both equations have in common? Frequency, okay? So, we are given the wavelength. We're given the wavelength. Frequency, we can calculate using the wavelength. And then using this frequency, we can calculate energy. Okay, so that's how you use both equations together, is when you're given wavelength or energy and you need to convert to the other, you need to go through frequency because that is what both have in common. Okay? So, what is the energy of a photon of light with a wavelength of 455 nanometers? First thing you need to do is our wavelength is in nanometers. We need to convert that to meters. Okay? Go ahead and do that for me. So you should get 4.55 times 10 to the negative 7th meters. Okay? That is our wavelength. Okay. Wavelength, we have the speed of light, that's a constant, okay, that's 3 times 10 to the 8th. So let's solve for frequency. So let's do 3 times 10 to the 8th equals the wavelength that we just calculated, 4.55 times 10 to the negative 7th, and we're solving for frequency, or nu. Okay, so I got this. This is a constant. We're using the equation C equals lambda times nu. Okay, so I have my constant equals the wavelength that I just converted times nu. Keep wanting to say V, times nu. Okay, so solve for nu. And you should get for the weight or for the frequency 6.59 times 10 to the 14th hertz. Okay, you now have your frequency. You now have everything you need to solve for the energy. H is Planck's constant, that's given to you, and we just solved for frequency. So, E equals Planck's constant, which is 6.626 times 10 to the negative 34th, times the frequency that we just calculated, 6.59 times 10 to the 14th. Okay? Multiply those together, and E should be 4.37 times 10 to the negative 19th joules. Okay? So a little recap. Wavelength and frequency. Our new constant here is capital C, or the speed of light, 3 times 10 to the 8th meters per second. Okay, so we have speed of light, wavelength, and frequency. Second relationship, we have frequency and energy. Energy equals a new constant, Planck's constant, times frequency. And then putting them together, understand that frequency is the thing that both of these have in common. Okay, frequency is the variable that both equations have in common, and you can use that to convert between the two.